This is Dreamtime Science, where tonight's most interesting discoveries become tomorrow's dreams. I've got something particularly engaging to share with you. You know what's fascinating? I've been thinking about how something as simple as a taste, like the tang of a lemon or the smoothness of soap, actually comes from tiny differences in the world of acids and bases. There's something remarkable about how these invisible qualities shape so many things around us, and I'm excited to quietly explore what makes them so different and special with you tonight. If this peaceful blend of science and serenity helps ease your evening, consider joining our community of gentle learners. Share your favorite moment of scientific awe in the comments. Before we begin, create your sanctuary, nestle into your chosen spot, let your muscles soften, and allow your breath to find its natural rhythm. There is a curious hush that settles over the world, just as the sun dips below the horizon, when the air cools, and the last golden rays scatter through drifting clouds. It is at this hour, somewhere between waking and dreaming, that our minds grow receptive to stories that blend the measured pulse of science with the elusive shimmer of myth. Tonight, let us embark on such a journey, following the winding path of acids and bases, a path that has taken humanity from ancient alchemical fables to the laboratories of modern chemistry, and from feverish legends of dragons to the sleek, cold corridors of science fiction spaceships. Let us imagine for a moment a medieval marketplace, alive with the scents of spices and the murmur of haggling voices. In a corner beneath a tattered awning, a bearded apothecary arranges glass vials filled with mysterious fluids, some the colour of garnets, others as clear as a mountain spring, some bubbling faintly as though stirred by an invisible hand. These are his potions, tonics, elixirs, and sometimes poisons. The townsfolk regard him with a mix of awe and suspicion, for his knowledge is arcane, his tools inscrutable. They whisper of his secret recipes, his ability to dissolve metals, to transmute base materials, perhaps even to conjure fire from water. This image, though shaped by the lens of legend, is less far removed from the truth than one might think. The roots of our modern understanding of acids and bases are deeply entwined with the history of human wonder and experimentation. The apothecary and his forerunners, the alchemists, were among the first to notice that certain substances, when added to others, produced heat, fizz, or even violent eruptions. Some transformed metals to powders, others etched glass or bleached cloth. The language of chemistry is still haunted by their ghosts. Vitriol for sulfuric acid, aqua fortis for nitric, spirit of salt for hydrochloric. Each name a whisper of the world's earlier attempts to grasp the hidden forces at play. Yet acids and bases were not merely the playthings of the wise or the wicked. They were, and remain, actors in the grand theatre of life itself. Within the sap of plants and the blood that courses through our veins, acids and bases maintain the delicate balance on which our very survival depends. But to understand their roles, we must first strip away the veils of myth and misconception and look clear-eyed upon what these substances truly are. At its heart, the tale of acids and bases is a tale of opposites, of partners bound together in a ceaseless dance. The ancient Greeks, whose language gives us the word acid from oxys, meaning sharp, knew acids by their bite, the sourness of vinegar, the sting of lemon juice. Bases, less obvious to the senses, revealed themselves in the slippery feel of soap or the bitter taste left by ashes. It would take centuries and the patient labour of many minds before the true nature of their opposition would become clear. The first clues emerged in the 17th and 18th centuries as early chemists experimented with the substances found in their kitchens and fields. They discovered that acids, when mixed with certain powdered minerals, would fizz and bubble, releasing invisible gases that could extinguish a flame or turn lime water milky. They noticed, too, that acids could transform blue plant pigments, like those in violets or red cabbage, into shades of red, while other substances, soon recognized as bases, could turn them green or blue. These color changes became the first litmus tests, precursors to the indicators we use today. But what, precisely, are these mysterious agents? What sets an acid apart from a base? The answer, as so often in science, lies in the invisible architecture of matter itself, in the subtle arrangement of atoms and the restless dance of their smallest components. Acids, as we now understand them, are substances that when dissolved in water release hydrogen ions, protons, the most diminutive and potent of all chemical players. The classical definition, given by the Swedish chemist Svante Arrhenius in the late 19th century, is elegant in its simplicity. An acid is a substance that increases the concentration of hydrogen ions, H+, in solution. Bases, by contrast, are those that yield hydroxide ions, OH, or otherwise reduce the concentration of hydrogen ions. Later thinkers like Bronsted and Lowry refined this view, defining acids as proton donors and bases as proton acceptors, a subtle but profound shift that widened the scope beyond watery solutions to include all manner of reactions. Yet, for all their scientific precision, these definitions do little to quiet the imagination. If acids are givers of protons and bases their eager recipients, then each chemical reaction becomes a kind of waltz, an exchange of invisible courtesies. Sometimes the dance is gentle, a mere passing of partners. Other times it is explosive, a rush of heat, a swirl of vapor, a sudden transformation of one substance into another. It is little wonder that, long before the periodic table, people saw in acids a flicker of elemental fire, and in bases a kind of earthly calm. Popular imagination, ever hungry for spectacle, has seized on the more dramatic aspects of this chemical choreography. Nowhere is this more apparent than in the realm of science fiction, where acids often take on the role of the ultimate destroyer, the liquid embodiment of entropy and chaos. Recall, if you will, the unforgettable scene from Ridley Scott's Alien, in which the blood of the extraterrestrial creature eats through the decks of a spaceship, hissing and smoking its way through steel as though it were mere paper. The image is so potent, so primal, that it has burned itself into our cultural memory. Acid, in this vision, is a dragon's breath made liquid, a force that brooks no obstacle. But how much truth lies behind this lurid fantasy? Can any earthly acid truly dissolve metal with such ferocity, or is this, too, a fable spun from the threads of awe and misunderstanding? Let us pause here, on the threshold of the real and the imagined, and peer into the heart of the acid mythos. The most powerful acids known to science, such as concentrated sulfuric, nitric, or hydrochloric acids, can indeed corrode metals, sometimes with alarming speed. The process is not magic, but chemistry. The acid's hydrogen ions snatch electrons from the metal atoms, breaking the bonds that hold the solid together. The metal is transformed into ions, which then dissolve into the liquid. Sometimes this process releases gases, hydrogen, for example, in the case of hydrochloric acid and zinc, leading to fizzing and bubbling that heightens the drama. But even the strongest acids are not universal solvents. Their power is selective, governed by the quirks of thermodynamics and the affinities of atoms for one another. For instance, concentrated sulfuric acid will char organic material, turning sugar into a blackened mass, yet it will leave certain plastics unscathed. Hydrochloric acid will dissolve iron, but not gold. Aqua regia, a legendary mixture of nitric and hydrochloric acids, is one of the few substances capable of dissolving gold itself, a fact that so impressed alchemists that they named it royal water, fit for the king of metals. Yet the cinematic vision of acid that eats through multiple decks of a spaceship in seconds is mercifully far from reality. In truth, even the most concentrated acids act far more slowly, and the materials used in spacecraft, often specialized alloys, ceramics or composites, are chosen precisely for their resistance to corrosion. What the movies offer us is not a documentary, but a dream, a distillation of our deepest anxieties and fascinations with the power of chemistry. Dragons, too, haunt the margins of the acid story. In medieval lore, the dragon's breath was often depicted as a stream of deadly vapor, capable of melting armor and stone alike. Some tales even hint at the dragon's blood as a virulent acid, a substance so potent that it could dissolve the very earth. It is tempting to see in these legends a kind of premonition, a recognition, however dim, of the transformative power hidden within the natural world. The dragon, like the acid, is both destroyer and creator. In the act of dissolution, it paves the way for new forms, new possibilities. Modern science has, in a sense, demystified these forces without robbing them of their wonder. The acids and bases that once seemed to belong to the realm of the supernatural are now recognized as essential tools, indispensable to industry, medicine, and the workings of life itself. Hydrochloric acid, for example, is found not only in laboratory flasks, but within the human stomach, where it helps to break down food and fend off pathogens. Sodium bicarbonate, baking soda, a mild base, soothes heartburn, cleans surfaces and leavens bread. The same principles that govern the etching of metals also underlie the metabolism of cells, the ripening of fruit, and the delicate balance of blood pH that keeps us alive. Yet, for all our familiarity, acids and bases retain a certain mystique. They are the agents of change, the catalysts of transformation. In the laboratory, a drop of acid can turn a colorless solution a brilliant pink, or precipitate a cloud of glittering crystals. A base can render grease into soap, or neutralize a venom. The breadth of their powers defies easy summary, spanning the mundane and the miraculous. There is, too, a romance to the language of acids and bases, a poetry that lingers in the names and metaphors we use. We speak of neutralization as though it were a truce between rivals, a coming together of opposites to create something new. The process is, in fact, a simple exchange. The hydrogen ion from the acid meets the hydroxide ion from the base, and together they form water, a union so fundamental that it underpins the chemistry of life itself. The salt that remains, a crystalline testament to their vanished differences, reminds us that every act of destruction is also an act of creation. Cultural associations have further colored our perceptions, often blurring the line between fact and fantasy. In literature, acids have served as symbols of purity and corruption, of danger and revelation. The acid test, for instance, originated from the use of nitric acid to distinguish gold from base metals, a metaphor that has since come to represent any decisive trial. In art and film, acids and bases are used to heighten tension, to signify power unleashed or secrets revealed. They are the hidden agents in detective stories, the tools of villains and heroes alike. Yet, for all their drama, acids and bases are not inherently evil or benign. Like fire, they are forces to be understood, respected, and when necessary, harnessed. The myths that surround them, of dragon's blood and alien bile, are in the end reflections of our own hopes and fears, our yearning to master the elements and to peer beyond the veil of the ordinary. As we drift deeper into this story, let us set aside the more lurid visions and focus on the subtle, intricate patterns that acids and bases weave through the fabric of the world. Their dance is not always violent. Sometimes it is as gentle as the ripening of a fruit, as quiet as the shifting of a pH in a pond at dusk. To understand these patterns, we must look more closely at the mechanisms by which acids and bases act, the ways they interact, the structures they shape, the balances they uphold. And so, with the echoes of dragons and spaceships still lingering in the air, we turn our gaze toward the heart of the acid-based tango, the molecular steps and countersteps that shape the chemistry of life and matter, unseen but ever present, guiding the transformations that make our world endlessly new. Let us slip now, quietly and curiously, into the subtle dance of hydrogen and hydroxide, and the curious scale by which we measure their interplay. Imagine, if you will, the gentle, constant hum of water all around us. Each droplet, whether in a teacup, a mountain lake, or the mist that lingers in the early morning, is a theatre for an ancient, invisible ballet. Here, molecules of water, simple H2O, are not as static or silent as they might seem. Even in the purest, most untouched glass of distilled water, a rare but relentless process unfolds. A handful of water molecules at any moment will split apart, a proton, H+, slipping away from one molecule, leaving behind a negatively charged hydroxide ion, OH, and joining another to briefly form a hydronium ion, H3O+. This quiet, ceaseless exchange is the foundation upon which our understanding of acidity and basicity is built. It is from this equilibrium, the balance between H+ and OH, that the elegant concept of pH arises, a scale so familiar and yet so often misunderstood, even by those who use it daily. The term pH itself is a relic of early 20th century chemistry, coined by the Danish biochemist Søren Sørensen. It stands for the power of hydrogen, denoting not power in the sense of force, but rather the concentration, the measure, the presence of hydrogen ions in a solution. It is calculated as the negative logarithm, base 10, of the hydrogen ion concentration. pH equals log 10 H+. This mathematical maneuver, a logarithm, serves to compress an enormous range of possible hydrogen ion concentrations into a scale running, for most practical purposes, from 0 to 14. It is a scale that, like a piano, can express both the thunderous and the delicate, from the acid sear of sulfuric acid to the gentle coolness of pure water. Consider a beaker of pure water at room temperature. Here, the concentration of hydrogen ions is 1 per man's 10 to 7 moles per litre, a number so small as to be almost unimaginable, and yet the logarithmic pH scale renders it into the pleasing integer 7. This number, 7, is the neutral midpoint of the pH scale, the dividing line between acids and bases. Solutions with a pH less than 7 are acidic. Those with a pH greater than 7 are basic, or alkaline. Yet, like all things in chemistry, this division is not a matter of simple boundaries, but of continuous gradation, of an unending spectrum. The pH scale, while simple in appearance, is layered with subtleties. It is logarithmic, meaning that each whole number step represents a tenfold difference in hydrogen ion concentration. A solution with a pH of 6 is 10 times more acidic than one at pH 7. A solution at pH 5 is 100 times more acidic than pure water. This exponential scale is the reason why small changes in pH can have dramatic effects, transforming benign substances into agents of corrosion or neutralization. But what of bases, those substances that are the chemical opposites of acids? Here the story deepens, for the pH scale is mirrored by another, pOH, the logarithmic measure of hydroxide ion concentration. In water, the product of the concentrations of hydrogen and hydroxide ions remains constant, a relationship known as the ion product of water, H plus OH is 1 per 10 to 14 at 25 degrees Celsius. This means that as the concentration of hydrogen ions increases, the concentration of hydroxide ions must decrease, and vice versa. The scales of pH and pOH are thus intimately linked. At any given temperature, their sum is always 14. If you know one, you know the other. Two sides of the same coin, locked in a perpetual duet. To appreciate the real-world power of pH and pOH, let us turn to the kitchen, that most familiar of laboratories. Here, the secrets of acidity and basicity are put to work every day, often without conscious thought. Take, for example, the humble lemon. Its juice contains citric acid, a molecule capable of releasing protons into solution, lowering the pH and rendering the juice sharply acidic, typically around pH 2. This acidity is not merely a matter of taste. It is the reason lemon juice can clean tarnished copper, dissolve the mineral deposits on a kettle, or lift stubborn stains from cutting boards. When lemon juice splashes onto a grimy surface, its acidity begins to break apart the molecules that compose the stain. Many common stains, such as those left by tea or coffee, are themselves weakly basic, or at least composed of organic molecules that are vulnerable to attack by acids. The protons donated by the citric acid disrupt the chemical bonds holding the stain together, fragmenting the molecules into smaller, more soluble pieces that can be washed away with water. This is not a violent process, but an elegant one, a kind of molecular negotiation between acid and base. Now, cross the kitchen to the baking cupboard and you will find another champion of chemical cleaning, baking soda or sodium bicarbonate. Unlike lemon juice, baking soda is mildly basic, with a pH around 8.3 when dissolved in water. Its power lies not in its ability to donate protons, but to accept them, to mop up excess acidity wherever it is found. When sprinkled on a sour-smelling carpet or inside a musty refrigerator, baking soda acts as a buffer, neutralizing acidic molecules that are often the source of unpleasant odors. The chemistry here is subtle but profound. Odors are usually caused by volatile acidic compounds, molecules that evaporate easily and tickle the nose with their sharp scent. When baking soda encounters these acids, a reaction occurs. The bicarbonate ion, HCO3, accepts a proton from the acid, transforming into carbonic acid, H2CO3, which almost immediately decomposes into water and carbon dioxide gas. The carbon dioxide floats harmlessly away, and the once pungent acid is rendered inert. In this way, the simple act of sprinkling baking soda becomes an act of chemical stewardship, restoring balance to the tiny ecosystem of the kitchen. But the relationship between acids and bases is not always so straightforward. The strength of an acid or base is not determined solely by its position on the pH scale. Here we must pause and examine a common misconception, that a high pH always signals a strong base, just as a low pH supposedly indicates a strong acid. The truth, as ever, is more nuanced. Strength, in the language of acids and bases, refers not to the numerical value of pH or pOH, but to the degree of ionization in water. A strong acid, like hydrochloric acid, HCl, dissociates completely in water, flooding the solution with hydrogen ions and driving the pH down towards zero. A weak acid, like acetic acid in vinegar, releases only a fraction of its protons. Most of its molecules remain intact, and the resulting pH is higher than that of a strong acid at the same concentration. The same logic applies to bases. Sodium hydroxide, NaOH, is a strong base because it dissociates fully, releasing hydroxide ions and driving the pOH down or the pH up toward 14. Ammonia, NH3, by contrast, is a weak base. It accepts protons only reluctantly, and the resulting increase in hydroxide ions is modest. Yet, if you were to prepare a very dilute solution of NaOH, its pH might be lower than that of a concentrated solution of ammonia. Thus, concentration and strength are distinct concepts. The former measures how much acid or base is present, the latter how completely it ionizes. This distinction is crucial in both chemistry and daily life. Consider the glass of lemon juice again. Its pH may be low, but as an acid, it is weak compared to the likes of hydrochloric or sulfuric acid. Its cleaning power is enough to tackle stains, but not so fierce as to corrode metal or scorch the skin. Similarly, baking soda is a gentle base, safe enough to eat, yet effective at neutralizing acids. The world is filled with such gradations, and the pH scale, for all its precision, is but one lens through which to view the intricate waltz of acids and bases. Let us dwell a little longer on the mathematical beauty of this relationship. The logarithmic nature of the pH and pOH scales means that their values can never be fully separated from the underlying equilibrium of water itself. If the temperature changes, so too does the ion product of water, and the midpoint of neutrality shifts accordingly. At higher temperatures, water ionizes more readily, and the neutral pH drops slightly below 7. This is a reminder that chemical concepts, much like the world they describe, are dynamic, context-dependent, and forever subject to the gentle influence of their surroundings. Even the word neutral is a kind of truce, a balance struck between the opposing tendencies of hydrogen and hydroxide. In pure water, the concentrations of these ions are equal, and so the solution is neither acidic nor basic. But introduce a solute, an acid or a base, and the equilibrium shifts, as if the dancers in our molecular waltz were nudged into a new formation. The system responds, always striving to restore balance, to reach a new equilibrium where the product of H+ and OH returns to its constant value. This ceaseless striving for balance is not confined to the laboratory or the kitchen. It is woven into the fabric of life itself. The blood that courses through your veins, for example, is buffered to a narrow pH range, around 7.4, by a delicate interplay of acids, bases, and salts. Were this balance to tip too far in either direction, the consequences would be dire, for the enzymes that orchestrate metabolism are exquisitely sensitive to pH. In plants, the sap that rises and falls with the sun is similarly buffered, for the machinery of photosynthesis and respiration depends on the careful management of hydrogen ions. Even the soil beneath your feet is a living laboratory of acid-base chemistry, as roots and microbes continually adjust the pH to favor growth or defense. And so, as you ponder the gentle power of lemon juice or the quiet utility of baking soda, know that you are witnessing the echoes of a universal principle. The pH and pOH scales are not mere numbers, but windows into the hidden negotiations that sustain the world. They are the ledger by which nature tracks the flow of protons and hydroxide ions, the balance sheet of chemical possibility. Yet, the waltz of acids and bases is not limited to cleaning and neutralization. There are moments when their interaction becomes dramatic, even explosive. When acids and bases meet in concentrated form, they can generate heat, bubbles, and sometimes violent reactions. But more often, the dance is slow, measured, and precise. It is the steady hand that guides the ripening of fruit, the leavening of bread, the preservation of food, and the very breath of life itself. As the night deepens and the hum of the world quiets, think of the countless molecules still moving, colliding, and exchanging partners in the silent theatre of chemistry. The pH and pOH scales continue their vigil, marking the rise and fall of acidity and basicity with each passing second. The waltz goes on, intricate and eternal, drawing us onward toward the next chapter in this story of balance and transformation, where the boundaries blur and the world is remade, one molecule at a time. Within the hushed chambers of the natural philosopher's laboratory, where glass reflects the flicker of candle flames and the scent of distilled spirits mingles with the sharp tang of unknown reagents, the story of acids and bases continues not only in the world outside, but crucially in the mind's eye of those who dared to probe their mysteries. The laboratory, with its array of flasks, vials, and curious contraptions, might seem a place of sterile calculation, yet it is in truth a grand ballroom, where the substances of the earth waltz and swirl, their transformations rendered visible by the keen wit and watchful eye of the experimenter. Here, the dance of acids and bases is not merely metaphoric. It is a carefully orchestrated performance, guided by the tools and techniques that have, over centuries, peeled back the veil on their hidden natures. Long before the precise language of pH and proton transfer, before the crystalline certainty of modern glassware, there was only the patient, sometimes perilous, work of observation. Alchemists, those early dancers in the lab ballroom, knew acids as spirits, aqua fortis, oil of vitriol, and bases as ashes and lies, their sharpness tamed in the crafting of soap. These terms, steeped in mystery, reflected not only the limited understanding of the substances themselves, but the very real limitations of the tools at hand. Glass was precious and fragile, balances were crude, and measurements were often matters of educated guesswork rather than precision. Yet these constraints did not stifle curiosity. Instead, they inspired inventiveness. Consider for a moment the humble litmus paper, today found in every school laboratory, a slip of filter paper imbued with the extract of lichens, its color poised to reveal the nature of a solution. The birth of this tool is itself a tale of careful observation and botanical inquiry. In the early 14th century, Spanish alchemist Arnaldus de Villanova first noted that certain plant extracts could change color when exposed to acidic or basic substances. Over centuries, naturalists refined this idea, isolating the dyes responsible, until the blue and red slips of litmus became the standard bearers for acid and base alike. Imagine standing, perhaps in the early 18th century, before a wooden workbench, a sheaf of freshly prepared litmus paper at your side. There, with a trembling drop of vinegar, the blue strip suddenly blushes red, a tiny transformation, yet one that reveals a profound secret, that there exists, in the invisible world of solutions, a property that can be coaxed into the open with the right test. In the presence of a basic solution, a dab of wood ash, dissolved in water perhaps, the red litmus reverts to blue, as if the molecule itself remembers its original state. This reversible dance is more than mere trickery. It is the visible sign of a deeper molecular negotiation, though the chemists of the time could only guess at what transpired beneath the surface. Such color changes, subtle and swift, became the foundation of qualitative analysis, and the laboratory soon filled with an expanding menagerie of indicators. Cabbage juice, cochineal, turmeric. The world's flora was conscripted into the chemist's service, each plant offering up its hues to the cause of science. Each indicator, with its own range of sensitivity, allowed the natural philosopher to probe further, distinguishing not only between acid and base, but among their varying strengths. The lab became a theatre of color, where the invisible properties of matter were made manifest in the spectrum's shifting shades. But color alone was never enough for those who sought deeper truths. The desire for quantification, how much acid, how strong a base, demanded new tools, new rituals. Enter the burette, a slender glass tube graduated with care, through which an experimenter could deliver a measured stream of one solution into another. The titration was born, a ceremony in which acid and base are allowed to meet, drop by drop, until the indicator signals their perfect balance. The endpoint, a flash of pink, a sudden disappearance of blue, marks the moment when all the acid has been neutralized by the base, or vice versa. From here, calculations can be made. The invisible strengths and concentrations are rendered tangible, numbers inscribed in the ledger of knowledge. The burette itself is a triumph of glass-blowing and precision, an instrument that would have been unimaginable to the earliest alchemists. Its invention in the late 18th century parallels the rise of quantitative chemistry, where measurement supplants mere observation, and the laboratory becomes a place of careful reckoning. In the dance of titration, each drop is a step, each swirl a turn upon the ballroom floor, the indicator acting as the orchestra, signaling the moment of resolution. Yet even as the tools grew more sophisticated, the mysteries deepened. The question of what is an acid, what is a base, lingered at the heart of the laboratory. It was not enough to see the color shift, to balance the burette, to tally grams and milliliters. The very essence of these substances remained elusive, their identities more inferred than understood. It is here that we encounter Robert Boyle, a figure so pivotal that the echoes of his work still reverberate in every chemistry classroom. Boyle, born in 1627, was a child of the English gentry, but his ambitions lay not in the management of estates, but in the cultivation of knowledge. His laboratory was a place of both wonder and rigour, a site where nature was interrogated with both scepticism and awe. Boyle's approach was methodical, his mind restless. He sought not the philosopher's stone, but rather the stones upon which true philosophy might be built. In his famed treatise, The Sceptical Chymist, Boyle challenged the reigning dogmas of the four elements, earth, air, fire, and water, proposing instead that matter was composed of corpuscles, particles whose combinations and rearrangements gave rise to all substances. But more than this, Boyle was among the first to treat acids and bases not as mystical agents, but as categories to be defined by experiment. Boyle's experiments with acids and bases were as ingenious as they were influential. Picture the scene, a table strewn with vials, some containing the spirit of salt, hydrochloric acid, others holding alkali of tartar, potassium carbonate. With a pipette fashioned from a goose quill, Boyle would add a drop of acid to a solution of plant dye, watching the colour shift from blue to red. Then, with a drop of alkali, the colour would return, proof that something was being undone, that the acid and base were not merely mixing, but somehow cancelling each other's powers. Boyle observed that acids shared certain properties, a sour taste, the ability to corrode metals, the power to change blue plant dyes to red. Bases, on the other hand, felt slippery to the touch, could reverse those same colour changes and restore the plant dye's original shade. He did not know of protons or electron pairs, but he grasped that these two classes of substances were locked in a kind of natural rivalry, each capable of undoing the effects of the other. It was Boyle who first articulated that acids and bases could neutralize each other, producing a salt and water, a concept so fundamental that it would become the backbone of all future theories. The drama of Boyle's experiments lay not just in their outcomes, but in the clarity with which he recorded them. He described, for instance, how the effervescence, the fizzing release of gas, could reveal the presence of an acid reacting with carbonate. He noted how the same acid might behave differently with different metals, or how the ash left after burning plants could be extracted with water to yield a substance capable of counteracting the sharpness of vinegar. Each observation was carefully logged, compared and analyzed, building a picture of acids and bases as distinct, interrelated categories rather than magical essences. Boyle's insistence on reproducibility, the idea that an experiment should yield the same result no matter who performs it or where, helped to transform chemistry from a secretive art into a public science. Tools like the balance, the retort, and in time the thermometer and barometer became the standard adornments of the laboratory, their presence a testament to the growing emphasis on precision and transparency. The lab ballroom, once a private stage, was open to all who could master its steps. As decades passed, the tools of the trade grew ever more refined. The glassblower's art flourished, producing vessels of exquisite delicacy, the Erlenmeyer flask's sloping shoulders, the volumetric pipette's slender grace, the beaker's squat utility. The chemist's bench became a landscape of possibility, each tool a passport to new realms of inquiry. When Justus von Liebig, in the 19th century, established his laboratory at Gießen, he equipped it with hundreds of pieces of glassware, each designed for a specific purpose, a testament to the increasing specialization of the field. But even as glass and measurement advanced, the experimenter's mind remained the most essential tool. It was intuition, curiosity, and skepticism that drove each new discovery. Clever experiments abounded. The splitting of water into hydrogen and oxygen by electrolysis, showing that acids could be generated at one electrode and bases at the other. The use of gas collection apparatus to track the subtle changes in volume and pressure that accompanied chemical reactions. Each new technique brought with it a fresh perspective, a new step in the dance. Consider for a moment the titration of a weak acid with a strong base, a procedure that, while now routine, reveals layers of subtlety. As the burette's contents drip steadily into the flask, the pH rises slowly at first, then more rapidly as the endpoint approaches. The indicator, perhaps phenolphthalein, colourless in acid, pink in base, lurks at the threshold, ready to announce the moment of balance. But the chemist knows that the curve of pH versus volume is not a straight line, but a gentle S-shape, reflecting the interplay between the acid's strength and its ability to resist change, a property known as buffering. Here, the tools and the underlying principles intertwine, each revealing more of the other. It is not only in the grand gestures that the secrets unfold. Sometimes a simple observation, a change in temperature upon mixing acid and base, the faint scent of ammonia released from an alkaline solution, can lead to new avenues of thought. The laboratory, for all its apparatus, is ultimately a place of attention, a space where the smallest detail may upend the settled order. As the centuries turned, the laboratory ballroom welcomed ever newer instruments, the pH meter, with its sensitive glass electrode, allowing chemists to capture the exact acidity of a solution in a digital display. The spectrophotometer, measuring the absorption of light to quantify the concentration of colored indicators with astonishing precision. Yet for all this technological marvel, the essential drama remains unchanged. The slip of litmus paper, the swirl of a burette, the fizz of gas as acid meets base, these are the rituals by which matter reveals its secrets, and by which we, in turn, come to know the world. In the flickering half-light of the laboratory, where the boundaries between past and present seem to blur, we see the procession of experimenters, Boyle, Lavoisier, Liebig, and countless others, each advancing the dance, each refining the tools and the steps. Theirs is a story not only of discovery, but of transformation, of substances, certainly, but also of human understanding. Each indicator, each flask, each clever experiment is a note in the grand symphony of science, a thread in the ever-unfolding tapestry of knowledge. And so, as the night deepens and the laboratory grows quiet, the tools of the chemist rest upon the bench, litmus papers folded in their envelopes, burettes emptied and rinsed, glassware gleaming in the lamplight. Yet their silent presence speaks of questions still unanswered, of experiments yet unimagined, of a dance whose final steps remain, for now, just out of reach. The ballroom awaits the next movement, the next revelation, the next bold partner to step onto the floor and coax another secret from the shadows. Beneath the surface of our everyday existence, a silent ballet unfolds, a dance choreographed by invisible hands, in the spaces between molecules, within the chambers of our bodies and the world around us. Acids and bases, so easily reduced in textbooks to formulae and numbers, are in truth the ancient architects of life's most intimate processes. Their interplay is not only the engine of chemistry, but the rhythm of living itself. To follow their trail is to pass through the ordinary and enter a realm where the familiar becomes mysterious and the mysterious becomes a mirror for our own complexity. Consider for a moment the unfathomable interior of the human body. Here, the tale of acids and bases is not abstract. It is lived breath by breath, heartbeat by heartbeat. In the warm, shadowed cavern of the stomach, for instance, the story begins anew each time we take a meal. The cells lining the stomach's inner surface stand as sentinels, their sole task to produce hydrochloric acid, a solution so potent that if spilled on skin or metal would burn and corrode. Yet here it is, conjured from the raw materials of our blood, pooled and churning in the name of digestion. This acid, secreted drop by drop into the folds of the gastric lining, lowers the pH to a level between 1 and 2, a seething cauldron where proteins begin to unravel, their complex structures untwisted into simpler strings that enzymes can snip and splice. The process is violent in its way, yet measured and essential, for without this acidic crucible, the food we eat would remain inert, its nutrients locked away behind chains of chemical bonds. The stomach's acidity is a gatekeeper, a first filter between the outside world and the inner sanctum of the body. But the story does not end with destruction. After the acidic torrent has done its work, the partially digested mass, now called chyme, is ushered onward into the small intestine. Here, the environment shifts dramatically. The pancreas, a quiet organ nestled behind the stomach, secretes bicarbonate, nature's own antacid. These bicarbonate ions neutralize the acidic chyme, raising the pH to a level where the next suite of digestive enzymes can perform their tasks without being denatured by acid. The balance is exquisite. Too much acid, and the intestine is overwhelmed. Too little, and digestion fails. Every moment, countless checks and signals ensure that acidity and basicity are matched, like two hands clasped in a perpetual handshake. Step back, and this process resembles a ritual cleansing, a passage from one world to another marked by the transformation of acidity into neutrality. It is an echo of the broader principle that underlies so much of biochemistry. Life thrives not in extremes, but in the subtle balance between them. This dance is not confined to the digestive tract. It extends, most crucially, into the very blood that courses through our veins. The human body is, in many respects, an aqueous solution, a walking, breathing container of water, salts, proteins, and suspended cells. Within this solution, the pH must be maintained with astonishing precision, hovering tightly around 7.4. A deviation of even a few tenths in either direction spells danger. The machinery of life is finely tuned, and enzymes falter if the environment strays too far from this narrow range. At the heart of this regulation lies the bicarbonate buffer system, a kind of chemical governor tirelessly at work. Carbon dioxide, a byproduct of cellular respiration, dissolves in blood plasma to form carbonic acid. This weak acid, in turn, can dissociate to release hydrogen ions, lowering the pH. The lungs, through the simple act of exhalation, expel carbon dioxide, tipping the balance back toward basicity. The kidneys, meanwhile, play a slower but equally vital role, adjusting the reabsorption or excretion of bicarbonate and hydrogen ions. Together, these organs engage in a continuous negotiation, a silent dialogue that keeps our inner world in a state of poised equilibrium. The consequences of imbalance are not mere abstractions. Acidosis, an excess of acid in the blood, can lead to confusion, fatigue, and, unchecked, to coma. Alkalosis, the opposite condition, brings its own cascade of symptoms, from muscle twitching to seizures. The body's survival depends on its ability to sense even the faintest whiff of disorder and to mount corrections with dispatch. This vigilance is not a conscious act. It is woven into the very fabric of our physiology. Yet for all its rigor, the body's management of acids and bases is not unique to humans. Every organism, from the simplest bacterium to the towering redwood, must contend with the same elemental challenge: how to harness the power of chemical transformation without succumbing to its perils. Plants, for instance, must manage acidity in their cells to optimize photosynthesis, while fungi secrete acids to break down wood and leaf litter. Even the ocean itself is a vast, living buffer, its waters absorbing carbon dioxide and modulating the pH on which marine life depends. Pause to reflect upon the scale of these processes. The same principles that govern the fizz of a lemon in your mouth or the sting of vinegar on your tongue are echoed in the cycles of the biosphere, in the rise and fall of tides, in the slow weathering of mountains. Acids and bases are not merely substances, they are agents of change, facilitators of birth and decay, the invisible hands that sculpt the world. In the kitchen their presence is subtle but pervasive. The sour tang of yogurt, the sharpness of fermented vegetables, the lift of a cake rising in the oven, all are manifestations of acid-base chemistry. Vinegar, citric acid, cream of tartar, baking soda, each adds its own signature to the symphony of flavor and texture. The sizzle when baking soda meets vinegar, the effervescence in a glass of sparkling water, these are not tricks, but the visible face of a deeper reality, the movement of protons, the rearrangement of bonds, the quiet work of transformation. In the garden, soil pH shapes what can thrive and what withers. Blue hydrangeas bloom only when the soil is acidic enough to unlock aluminum ions, painting their petals with hues that would be impossible in alkaline earth. Farmers and gardeners test and amend their soils, coaxing the right balance from the land, knowing that too much acidity stunts roots and too little locks away vital nutrients. The health of forests, the yield of crops, even the color of flowers are dictated by the unseen dialogue between acids and bases. On a still more intimate level, the chemistry of acids and bases is written into the language of sensation. The burn of a chili pepper, the astringency of underripe fruit, the puckering shock of lemon juice, these are signals, honed over millennia, that guide our choices and safeguard our bodies. Acidic environments can be hostile to pathogens, and the taste of sourness is often a warning of spoilage or danger. Yet, paradoxically, it is also a source of delight, a craving that finds expression in cuisines the world over. Even our emotions, it seems, are not untouched by this chemistry. There is an old metaphor that likens bitterness to sorrow, acidity to sharpness of feeling, sweetness to joy. Language, in its wisdom, has borrowed from the palette of taste to describe the spectrum of experience. It is as if the body's ancient dialogue with acids and bases has left its mark on the mind, shaping how we speak of pleasure and pain. Philosophically, the ubiquity of acids and bases invites a kind of humility. For all our sophistication, we are at root chemical creatures, our thoughts and dreams afloat on a sea of fluid, buffered and balanced by the simplest of particles. The elegance of this arrangement, its resilience, its adaptability, suggests not randomness, but a kind of order, born of countless generations of trial and error. Life, it seems, has learned to thrive not in spite of the caprices of chemistry, but because of them. Reflect on the notion of homeostasis, the tendency of living things to maintain a steady internal state. The regulation of pH is a paradigm of this principle. It is a process of constant adjustment, 1,000 tiny corrections made in response to shifting inputs. There is a lesson here for those who seek certainty or finality. Stability is not the absence of change, but its management. The body does not aspire to stasis, but to dynamic equilibrium, the ceaseless balancing act that allows for growth, repair, and adaptation. In the grand theatre of existence, acids and bases are never still. They are always becoming, always reacting, their identities in flux. A hydrogen ion released today may be taken up tomorrow. A buffer molecule may serve as acid in one moment, as base in the next. The boundaries between categories blur, and what matters is not the label, but the relationship, the continual exchange that sustains the whole. The insight is both scientific and poetic. The world is not made of fixed things, but of processes, of patterns that endure through change. Acidity and basicity are not properties held in isolation, but potentials revealed only in interaction. Each moment of balance is achieved anew, the result of innumerable contests and alliances at the molecular scale. And so, as you drift into the quiet spaces of night, imagine this ceaseless interplay continuing, unheralded, beneath the surface. In the cells of your body, protons move along chains of amino acids. Enzymes shift their shapes in response to tiny changes in pH, and every part of you is engaged in the work of preservation and transformation. The world beyond your window, too, is alive with this same chemistry, the damp earth breathing, the rain falling, the air itself alive with potential. To know acids and bases is to glimpse the deep logic of life, a logic built not on opposition, but on complementarity, on the give and take that makes complexity possible. The most ordinary things, breathing, eating, tasting, growing, are revealed as miracles of coordination, each dependent on the most fundamental exchanges of matter and energy. There remains, always, mystery. For each process we unravel, new questions arise. Why does life choose the balances it does? What hidden harmonies have yet to be discovered? What subtle dances elude our instruments? The chemistry of acids and bases is an open book, its pages still being written, its meanings waiting to be found in the spaces between the known and the unknown. Thus the dance continues, unending and unresolved, a gentle tide that ebbs and flows within and around us, connecting our smallest parts to the vastness of the world. And in this dance we find both our origins and our destiny, suspended in the delicate equilibrium that is the hallmark of life itself. As our gentle journey through the shimmering dance of acids and bases drifts to a close, we watch their subtle reactions fade like a comet tail into the hush of space. May this quiet wonder linger softly in your thoughts, inviting peaceful curiosity until we meet again beneath the starry veil for more Dreamtime tales.